with the lab. We'll have some discussion on that, maybe even tomorrow when everyone's back. But then we will also have, you'll also have time to then work on the next topic, which, as it turns out, is actually pretty simple. And our next topic is power, electrical power. Okay, so electrical power is not really that different from previous definitions of power. So let's start there. What was power from last semester? Work over time, right. So power last semester was an amount of work over time. What units did we use to measure watts? 1 watt, and then we had work, which is joules, time a second, so it's a joule per second. We're going to do it the same way electrically. So at some points, you might have to think back to how we defined work with an electric charge and apply that here. But there's another way to find this too with some of the characteristics that we started talking about last week with Ohm's law and with our the measurement of resistance. Yes?
What's the symbol for watts?
Capital W.
What's the symbol for work?
Capital W. So the way that we can see this, we've got joules per second up here. We've also come across those units with some of our other characteristics, namely, which of the electrical characteristics involve joules?
The one to the left, is that power equals watts divided by time?
Work over time.
Okay.
Which of our electrical characteristics, though, involved an energy, or joules?
No,
Not current, but you're on the right track now.
Wasn't it volts?
Volts is the energy in a circuit, right? And so we had 1 volt is equal to a joule per coulomb. Now current was in there too. What do we measure current in? Amps. It's not joules per second.
Coulomb per second.
Coulomb per second.
If you multiply them together, you get this.
Bingo. If we multiply this by this, we get that. And that is the definition for, or the formula for electrical power. It amounts to the same thing. It's still measured in watts, which is the same as a joule per second, because when we multiply a volt by an amp, we get a joule per second. But this is a really slick way to use what we've already learned from electricity. Let's combine this so we can see it with Ohm's law. And Ohm's law was V equals I times R. We're going to start applying that a lot this week to different circuits and things. But that's voltage is equal to current times resistance. Well, I just want to take this and substitute it in, because that gives me a different way to measure voltage, or at least define voltage. I can also take the current going through something times its resistance. So that means I could rewrite this by substituting that in. I'd have I times R, which simplifies to I squared times R. So that's an equivalent way, just what might save you a step sometime. Likewise, if I solved my Ohm's law for I would get I is equal to V over R. Substitute that in for I could also write this, instead of I, I'd have V over R times V, so that'd be V squared over R. Those are two equivalent ways to get to the same thing, but it might save you a step depending on what you're looking at. One last thing before we move on. What did we define in words power to be? We've sort of already defined it by the formulas, but
An answer, yes. Work over a period of time,
it is.
but you want it more wordy, don't you?
Yeah, we want a nicer prose.
Let me put this poetically.
Yeah. Flex your poetic muscles. I'll just remind you guys. It's the rate that work is done, is what we had defined it as. What did we define work as in prose? Yeah, not just a force through a distance. There was another, a little more poetic way of saying it. There are many good physics poems.
The act or amount of adding or removing energy.
Adding or removing energy, that's good. Essentially, since the conservation of energy says we can't create or destroy energy, what work is it's just changing the forms, right? Often we would say that that's adding or subtracting energy from a thing, and that's doing work on that thing. But really what we're doing is we're taking energy from one object or field or whatever and putting it into something else, or vice versa. So power here is the rate that we're changing forms of energy from one thing to another, from one type to another. Consider this with a light bulb. We start out with energy in the form of electrical potential. So the electrons have some potential energy. We push them through a light bulb. What do we convert that potential electrical energy into through the light bulb? Light and heat. Oftentimes we say that this power is being used or it's consumed because that light and heat, realistically, we can't get back. It's going into the surroundings. It's causing everything there to heat up, but it's very, very hard to get it back. So it's sort of being used up. So just some terminology that you'll encounter throughout the chapter and later on is that power is sort of the rate that we're losing energy. So if you've hooked up a battery to something, or if you're looking at electrical usage, it's how quickly is it being transferred into heat, mostly. And then once it's heat, we can't use it anymore. Mm-hmm.
So when it's day, the sun puts energy in an atmosphere. Why does it get cold? Like, where does all the heat go?
Oh, at night?
Yeah.
Back into space.
There's nothing in the space to go to.
But it can still go. It doesn't have to go to anything. It just radiates. If there were no sun, if there were no light, we could still potentially detect all of us in this room by looking at infrared. Because everything that is above absolute zero, as I heard coming in, is emitting radiation to its surroundings. It just so happens that if something is not real hot, we can't visibly see it. That radiation would be infrared or even, radio waves. When things are hot enough, they start to glow in the... No, not as hot as Cade.
No, I mean, like Mayor Dowd used to say something.
Oh, that's fine. We'll get there. When things are really, really hot, then they start glowing visibly. And that's what a light bulb is. So the filament gets very hot, maybe thousands of degrees. And when it does, it glows. Metal that's hot starts glowing kind of cherry red, but if you keep heating it up, it glows bright more and more towards the other end of the spectrum. And eventually you kind of see all the colors because the peak is somewhere in the middle, and it glows white. Anything that temperature glows like that, and it's changing that thermal energy into heat that it radiates out.
Even water.
Even water could, yeah. Anything. That's how we can tell how hot other stars are, because we look at where its peak color is. Mm-hmm.
So if you cool something down enough, will it eventually turn like black, like a shadow? So we couldn't see it?
Certainly yes. I mean, black things don't, like your black tabletop, doesn't reflect too much light, which is why it's black in itself, and we can't see the form of energy that it still does radiate. We could feel it as heat, but we can't see it because it's not nearly hot enough. And you can get different finishes and different things like that absorb even more. A big part of early quantum mechanics was based on discussion of a black body, which is something that absorbs all of the energy that hits it.
So you know how like colors, like not everything's just a solid color, like does that mean like different parts of object are absorbing different amounts of light?
It would, in that case, yeah. I'm not sure I understand.
In our vision, like we don't just see like just green, like solid green.
Well, yeah, very often it's reflecting only a few wavelengths, which our eyes sort of mash together into the color that we see, like pink. Pink doesn't occur except as a mixture of other colors. Okay. We have a problem set on this and some suggested reading to go through too. It's really fairly straightforward as far as things go. So we've got some time to work on that today. We also have time to finish up the lab, the Plato lab. I know some groups finished up the data taking, maybe every group, but a lot of groups still need to work on the analysis and conclusions. So we'll have time to discuss that as well. And hopefully some time for Tom to get shocked.